So this time, because I don't trust my senses, I'm going to do this in the reverse order. We're going to go first principles first, and then we're going to draw ourselves a picture. You always must ask the question, when you get a result like this, right? Well, what does it mean? And as you will notice, there's actually something important, a sort of, what's the word I'm looking for? Like almost a disclaimer that you need to make after you go through first principles, because there's something first principles won't necessarily tell you. So let's give this a go. If this is the function, right, then its derivative by definition is the limit as h approaches 0 of, and off you go, you start reciting, right? So this is f of x plus h, right? Here's f of x, and then of course you divide by h because that's the run, okay? Now you're not used to this all that much because you're like, what do I do with this? You know, I could expand brackets, I could add fractions. What? Okay, now, that's alright, surds, they are notoriously antisocial, but that doesn't mean you can't work with them, right? We're used to rationalizing denominators, so on the top, no problem. Just rationalize the numerator, right? What am I going to need to multiply by? X plus h plus. Now, this guy, you might remember, has a name, starts with C. You remember? Long word. So close, so close. These two guys are called conjugates of each other. Conjugates. Conjugates come up again and again and again. When we get to complex numbers at the end of the year, conjugates will reappear. Fantastically useful thing. So the reason why we can use conjugates here is because you're going to get difference of squares up here at the top, right? This is really an a minus b times a plus b situation. So once you expand difference of squares, you get the difference of two squares, a squared minus b squared, right? So I've got my limit, and here's a, so a squared will be this, right? That's a squared. Take away b squared, right? That's b squared. A squared minus b squared. I'm done. That's the crucial step. Now I do have all of this garbage over here on the bottom. But that's okay. That's okay. He'll come out in the wash, right? So now, and you're starting to get the trend, right? In order to evaluate first principles, you're always getting something on the numerator that's going to dance with this h on the denominator, right? If you don't, then something is going wrong in your algebra. But here we're okay. X and negative x go. The h's go, right? So really all I have is this. Yep. Now I can actually evaluate, like so. So I've got two of those. Okay, now let's just check this out. Let's just check this out because we have a rule. Let's see if the rule can handle not just negative indices, but fractional indices. If we replay, right? How do you rewrite root x in terms of powers, indices? X to the half, right? X to the half. So all I need to do is bring that power out the front and reduce the power by 1. Yeah. Which, sure enough, that means you're going to go on the denominator, right, to root x. Ooh, that was easy. Okay, now, what does this mean? What's this thing look like? Okay, so here is my set of axes. You can see I've only got, I actually don't even need that. I only need that. Okay. What's the square root of x look like? It's half of a sideways parabola. Yep, half a sideways parabola. There is the square root of x. Okay. What's 1 on 2 root x? What does that thing look like? There's an asymptote, isn't there? Yeah, because number one, I actually have two asymptotes, just like earlier. First, you can't put in x equals 0 there, can you? Because it's on the denominator, right? So I'll just leave it. I've got this guy at x equals 0, right? But not only that, as I put increasing numbers, like as x approaches infinity, right, over here, the denominator is, well, it's not exactly skyrocketing because it's the square root of x, so it slows down, but it's still getting bigger forever, right? So being that it gets bigger forever, it's going to approach 0, right? So there's my horizontal asymptote there. And in order to fit into these two things, that's pretty much all you can do.
But so like if you find the y, so it's like half.
There aren't any ways.
So it's like
No intercepts. Look, Ma, no intercepts. Okay. Yeah, I guess so. Except you would have to then, if you have the squared, you'd have to restrict the range. But that would be fine. There you go. That's what it would be. Because you'd you'd get this other side over here, which.
no, it's not. But you would thought.
Does it match what you expected?
Kind of, because it's like decreasing.
Yeah. So this graph, right, the original one, square root of x, it is. Let's think about its gradient. It's increasing all the time, right? It slows down. It slows down forever, in fact, but it never slows down so much that it turns around. Okay, that it turns around. Now, one of the ways you can know that is because to turn around, this gradient would have to at some point equal 0. Do you agree with that? Right? But there's no value of x you can ever put in here to make the whole thing equal 0. You can get very, very, very small, but you'll never actually get to 0, right? Which is why the square root of x never turns around. It's positive. This remains positive. It checks out. That's all there is to it.